Okay, well, thanks for the invitation today. And when I first signed on to volunteer to give a talk, I think I gave the title something like "What's WPC up to lately?" Because I really didn't have a topic. I figured I'd come up with something. But in the process, in the couple of weeks, several weeks since that initial invitation, I've been preparing for the National Winter Program meeting that will take place virtually next week. I think it's Tuesday through Thursday next week. Most afternoons, it's about a half day. And there'll be regional representatives at the meeting. There'll be headquarters folks. Of course, we know Dr. Uccellini as director is incredibly interested in winter weather and tracks what's going on. So I think he'll make an appearance. And so these are my slides for that section of the meeting next week, where I was responsible for providing a seasonal review. And as some of you may know, I spent a lot of time generating different maps and graphics as kind of a hobby of mine. So without further ado, let's just take a look at snowfall, snow anomalies, primarily using no-risk data over the United States. So this was the October through April timeframe, 2019 through 2020, using the no-risk snowfall analysis, the 12Z to 12Z 24-hour totals, and basically just summing them for that period of time, 122, I don't know how many days are in there, 150 so days. And, I don't know if there's anything too shocking on this until you see the departures in a second, but, I saw amounts upwards of 10 to 15 feet, quite common, especially downwind to the Great Lakes and the higher elevations of New England, and also across the Rockies, the Sierra Nevada, and the Cascades. If you go to the next plot, we now have 11 years of data, gridded snowfall data from NOAA. So we can do departure maps or means. This is the mean over that same period of time. And maybe if you want to toggle back to the first one and this one, you get some idea of, and I'll show you a departure map in a minute, but you can certainly see that, the mean's a little smoother than the current season. And then if we go to the next slide, you'll see the departures here, which are kind of striking in the east. Well below normal snowfall for the period from October through April across the Appalachians, even downwind of Lake Ontario, normally a pretty snowy area. It doesn't take much to get snow in the lee of the lakes, as we know, and the Great Lakes. But well below normal, over 3 feet below normal along the spine of the Appalachians there and up into upstate New York. And also just a real lack of any kind of coastal. There were coastal storms, but the precip type was normally in the form of rain from New York City up through Boston and down East Maine. Well below normal snowfall in these areas, basically very little snow falling in some of those areas, resulting in departures of well over 3 feet for the season. Across the central region, and we're going to look a lot more at central region in just a minute here, kind of a mixed message here. Some areas below, some above, perhaps the swath with the greatest anomaly. And again, this is just a decade of snowfall. We're not looking at a long-term mean here, but a decade of the gridded data is now available. Certainly some notable snowfall events, basically from Wyoming, the Front Range of Colorado, across western portions of South Dakota and Nebraska, up into eastern North Dakota, where amounts were about 3 feet or a little above 3 feet above the long-term norm. And then also the UP of Michigan showing well above normal no-risk amounts there for the season. The Rockies overall, well below normal in the Sierra, northern Rockies, below normal snowfall. The Cascades, especially in Oregon, showing well below normal snowfall there. So the next slide. This is just a review using the Iowa Mesonet for the base data here, just looking at winter storm warning days for the period December through March. So kind of tightened up the season a little bit here, dropped October and November from the analysis and just looking from December through March. Winter storm warning days from the Iowa Mesonet site that does this plot is my plot, but the site does do plots, but they weren't quite the time frame that I was looking at, so I took the raw data and plotted it here. And no surprise, you don't see a lot of winter storm warnings in the south, so that's not much of a surprise there. If you go to the next map, we can take a mean of these over the same period of time over the past 11 years, and then the departure map basically shows us where some offices might have been a little busier than others as far as winter storm events this past season. Again, coinciding with the below normal snowfall that we saw in the east, well below normal number of winter storm warning days, basically in the mid-Atlantic region of the Appalachians, Pennsylvania, up through parts of Michigan and Ohio. I would say well below normal across the Ohio Valley. But then again, there's that swath across central region, 14 more winter storm warning days above normal for Cheyenne's area, and then parts of the Dakotas and up into northeast Minnesota as well. So you were busy, no question about it, and we're going to look at a little more detail at the amounts there next couple of slides. So go to the next slide. So the following maps are basically a monthly bulk snowfall forecast analysis, and the map key here is that we start with the observed snowfall for the entire 1 month period, again using 24-hour snowfalls summed for the month from no risk, and then look at WPC's 24-hour forecast issued at 12 to 12Z, basically matching that observed snowfall summed over a 31 day period, and the same with the NDFD's forecast. And NDFD, no risk, WPC are all regridded to a 5 kilometer grid to match so that we can do difference fields in the bottom. And the bottom row basically showing the difference between the WPC deterministic snowfall and the NDFD snowfall. Again, 24-hour forecast valid 12Z to 12Z and summed for the monthly periods that we're going to be looking at. And then the difference between the WPC forecast and the no risk, and the difference between the NDFD and the no risk. I do want to say that there's certainly questions about no risk as far as its value. It's valuable as far as its verification capability. I know some areas have more of a challenge using no risk than others, especially in the mountains. I'm not going to spend a lot of time looking at the verification numbers in the mountains. They're very noisy, and so I'm going to focus primarily on those areas that are a little cleaner. I did do some spot checks on the no risk totals that resulted from this analysis, and they look reasonable, but your mileage may vary. But it is only it's really one of the few data sources that we have, and we verify QPF in a similar manner with gridded data sets that are remotely sensed and derived. So take this with for what it's worth, which is we're assuming we have some semblance of truth with respect to no risk, but there are flaws in that analysis, and so we have to keep that in mind. So if we go to the first month here, looking at the month of December, I think 2019, again, analysis, forecast summed for 31 days there at the top from WPC and NDFD. What's kind of neat about these analyses and the forecasts is you can definitely see different storm systems and storm tracks, and then of course the favored regions for really heavy snow, especially downwind of Lake Superior there. And then the differences are interesting too. I mean, one signal that I see consistently from season to season, I've been doing this now about three years, is that WPC tends to be not quite a bit, but somewhat more conservative in the snowfall amounts when compared with NDFD. I'm talking about the lower left graphic here. So that the darker browns there are where WPC is under forecasting the NDFD. In the difference fields, it's kind of interesting. Another characteristic that shows up pretty consistently, not for everywhere, but generally the pattern is that the NDFD forecasts tend to be a bit aggressive with respect to the no risk. WPC's error fields are kind of a mix between under forecasting and over forecasting. You don't see as much of that under forecasting going on in the NDFD, although it does show up. You see it there a bit in the Northeast, and you see some parts of eastern North Dakota, and even in the UP of Michigan, a few under forecasts with respect to no risk. So that was the month of December. We'll go into January 2020 as the next slide. Same setup here. And again, we see that the WPC difference from NDFD in the lower left shows a tendency for WPC to be lower than NDFD. I could not calculate mean average error on these graphs on a national scale, and so I didn't spend a lot of time looking at the actual grid analysis of this data. Part of the problem I had was there were a number of NDFD grids, for example, South Florida, that would corrupt the analysis because they were set too high. I have to go in there and play around with that to get that to change. But anyway, the same character that we saw in December, kind of a mixed message across the plains and the Midwest with respect to under and over forecasting. NDFD tends to have more of a high bias in terms of the forecast than the WPC. And again, the mountains, well, I'm not even going to go there. There are some issues, I think, with snow liquid ratios in the West, and I think that probably played a role in a large amount of over forecasting across the Western United States, especially in the mountains. There are pretty remarkable improvements overall, though, given that WPC is now in GFE and generating grids that are a much higher resolution than they had been doing in the past. So we're seeing some improvements there, and some work that Bruce Veenhuis has just finished up is also showing some really good scores in 24-hour snowfall forecasts. And I think a good part of that is because of the improvement in resolution. If we go to February, more of the same here. I love the pattern in February. You can definitely see the storm tracks, the different storm events across the central United States, and even across parts of the Appalachians and Mid-Atlantic. Those are each individual storm events that occurred at some point during the 29 days of February. And again, we see the same characteristics appearing in the difference fields, slight under forecast, slight difference, lower amounts of snowfall forecast by WPC as opposed to NDFD. The pretty decent forecast, though, overall. I think the errors are pretty low here for the month of February, and some pretty good forecasts occurring in February. And I think did I include March here? I'm not sure if I have March on the next one or not. Yeah, so here's March, and again, not much here other than the same characteristics that we saw. WPC tend to be a little bit lower under forecasting events across the Central Plains and parts of the Western Great Lakes compared to NDFD. So now let's zoom in on Central Region, and let's zoom in over the entire December, January, February, March period. And I think the striking thing here is the large difference between WPC and NDFD when you sum all of these forecasts up over 122 days. I think there were 2 days missing from the data set where I didn't have NDFD data. I think it was March 24th and 25th. They're not included in the analysis. I don't know if anything happened on those days, but they're not in here. So this is a summed snowfall analysis of forecasts and verification for the 122-day period. And it is quite striking. You know, you're getting amounts there in aggregate of a foot to even locally 2 feet, where WPC is under the NDFD. If we go all the way over to the lower right, you can see, however, that the NDFD in those same areas is over forecasting events by about 1 to 2 feet. But still, in the mean, WPC's snowfall forecast in the Great Lakes and upper northeast portion of Minnesota there, well below what was in the no risk. But more of a balance. So it's like more of a balance between the over and under forecasting and the tendency in the NDFD to over forecast based on no risk. Next slide. I'm going to go into some. So what I did was sum up the snowfall from no risk, sum up the snowfall for the season or the December through March period from NDFD, and sum up the entire amount from WPC forecasts. Again, all 24-hour forecasts were used here. And I use these locations, which are essentially the centroid of these CWAs. Again, not going to go in the mountains. I could do the same thing there, but I decided, Boulder, Cheyenne, we're going to have to look at those a little more closely, obviously, because the centroid of your CWAs may be at 10,000 feet or 12,000 for all I know. But these are the summaries showing, again, the same characteristic that we saw in the difference fields, where there's a tendency for NDFD to be a bit hot when compared with no risk. If you go to the next slide, basically the mean of these CWAs shows up here. And I was quite pleased, actually, to see that the deterministic snowfall forecast from WPC was a good match with what no risk had in the mean. And again, that characteristic, a bit of a high bias for the NDFD forecast in the mean, about 40 inches observed and about 30, 35 maybe. So we're going to start looking next at a breakdown of the probabilistic winter precipitation forecast from WPC. These are, the input values for the prob snow. And so the question you ask here is, for an observed snowfall event, for a 24-hour snowfall event ending at 12Z, where did that snowfall event fall within the ensemble distribution in the PWPF? And a calibrated ensemble, you'd kind of want to have half of your events fall within the interquartile range. You'd want to have 25% of them occur below the 25th percentile rank, and 25% occur above the 75th percentile rank. And we see quite a bit of variability here, but again, the next slide just highlights the mean, which shows that we're relatively well calibrated in the PWPF, where we're seeing about 43% of observed snowfall events falling within the interquartile range of the ensemble distribution. That's not a bad number and is relatively consistent with prior years away from the mountains, with 17 events being the mean. You can see snowfall event. This is where an observation and or any one of the forecasts equaled or exceeded 1 inch. And so Marquette gets the prize in this distribution of CWAs with 45 events meeting that criteria. And a tendency in Marquette for snowfall events to verify a little bit higher on the higher end of the distribution. So a little bit of an offset there with 42 events verifying in the upper 75th percentile rank. So a little hot there. Can look at this in a little more detail. I chose on the next slide Topeka with 10 events, because this makes it really nice to describe. With 10 events, you should see about 5 of those events occurring in the interquartile range. And then two or three above and 2 or 3 below. And right off the bat here in Topeka, you see the first 2 events identified: December 14th with a 2-inch snowfall and the no risk, and December 15th with about a 6.5, 7-inch snowfall, the blue dots there. Those events occurred completely outside of the ensemble distribution, so above the 75th percentile rank. And those are the types of events I think we'd want to take a closer look at and say, well, what the heck is going on there, where you had a 6.5-inch snowfall? And WPC and NDFD were in line on that December 15th event with maybe forecasting just under 3 or around 3 inches of snow, the white dot being the WPC forecast and the red dot being the NDFD forecast. And that would be a safe bet in most situations, because you should be able to, if you forecast in the interquartile range, you should be able to verify about 50% of the time. So that's a safe and it's a good forecast, but it verified at about double that amount. And then you can see that just the character of the forecasts for the rest of the season. No real significant snowfall events here after that December 15th event. But the distribution is about 20%. And I want to say I did the 90th percentile there. Yeah, I broke it all the way down. I did 90th, 75th, interquartile range, below the 25th, below the 10th. And so, with a 60% of the events verifying within the interquartile range, it's a reasonably well-calibrated ensemble for the events that occurred here in Topeka. And then we go to the other side of the scale on the next slide, taking a look here. at the many events, the 39 snowfall events that occurred in northern lower Michigan at the centroid of the CWA there. And I think these say above, this one was charted for at or above 0 inches. I've got to check on that to see if I encompassed all events. It looks like I may have done that. But even here, if you do the aggregate, if the sum of all of these events, you still see that, if you're using the interquartile range to predict your snowfall event, and it is frustrating. Deterministic forecasting is, people want a number, but we know that it often should be a range. But if you're in that interquartile range, you've probably got a pretty decent shot on, certainly a coin flip. If you add some skill to that, you should be better than a 50% chance of ending up within that range. I'm really intrigued by this January 11th event, which is kind of in the middle of the plot here. A huge range in the ensemble, basically 24-hour forecast showing a range anywhere from just above 3 inches to over a foot. The forecasts were appropriately in the middle of that range, about just over 6 inches, and the no risk came in at just under 3. So and wasn't even in the distribution of the ensemble. So this particular event is really interesting to me, and I did quickly go back and look, but I'm not quite sure what contributed to such a large range in a 24-hour forecast. And I'm also interested in doing a little more work on these interquartile ranges and trying to understand, the means and the extremes with respect to the snowfall ranges. And then I think that just about sums it up here. The winter summary for next week will emphasize the fact that we had much below normal snowfall in the east, well above normal from Wyoming, parts of the Front Range across the northern plains, number of winter storm warning days below to much below normal, especially in the east. The bulk analysis reveals WPC snowfall is lower than NDFD in many cases. And there are also cases where, when we have decent agreement between WPC and NDFD, you can see those as well in some of the difference plots. The mountainous terrain in the west is going to remain a complex problem, especially with respect to not just with respect to forecasting, but also with respect to verification and using the no risk analysis. And from what I can tell, using the ensemble forecast is definitely the approach we should be taking. They do seem to be reliable. I think that we will be seeing much more of a inspection of probabilistic snowfall forecasts, especially with the use of NBM now. I think NBM is doing well as well, but I didn't have all the NBM data, and they changed versions through the season, so was not able to verify against NBM, but look forward to do that in the future. So thanks again for the invitation to present today, and I think there might be a little bit of time for questions.